Okay. Good afternoon, everyone. Thank you for joining us today for our third session of Hi-DARS Fall 24 Talk Series. I'm Bahar, and then on behalf of Hi-DARS, it's my pleasure to welcome you to this lecture here at Texas Tech University's Huckabee College of Architecture. We're excited to host today's lecture both in person and online as part of our Fall 24 series. We're honored to have Dr. Milad Showkatbaksh with us as our guest speaker. Dr. Showkatbaksh is the co-director of Emergent Technologies and Design. Hello, okay, much better. Where was I? Dr. Milad Showkatbaksh is the co-director of the Emergent Technologies and Design postgraduate program known as EmTech at the Architectural Association School of Architecture. His work is at the intersection of architecture, ecology, and computational design, where he explores the transformative potential of biological intelligence and algorithmic methods in urban design and digital fabrication. With a background that spans architecture firms across Asia, the US, and Europe, Dr. Showkatbakhsh has established himself as a design technology specialist. His research includes his widely recognized PhD work on homeostatic urban morphologies. He's also the co-founder of Wallasey, an evolutionary and analytic engine for Grasshopper 3D, which continues to push the boundaries of computational design and fabrication on both architectural and urban scales. Today, Dr. Showkatbakhsh will share insight into his work and research delving into how computational methods can harmonize architectural design with ecological systems. I'm sure we're all eager to learn more about these innovative approaches and the impact they have on the future of architecture. Following his presentation, there will be time for a Q&A session, so please hold your questions until then. Let's give a warm welcome to Dr. Milad Showkatbakhsh, and thank you for joining us. The stage is yours.
Thank you for having me and for the kind introduction. If you see my screen, I'm just gonna dive right into this. I was kindly introduced by your team. I'm the co-director of the EmTech program at the AA in London, but I actually did also my PhD a couple of years ago, and now working there and pursuing the research. All right. I want to talk about architecture, but from the perspective that we perceive this discipline, and this is something that has been at our attention for a long time here at EmTech. This is the discipline that is going through evolution and is extremely aligned with the advances in technology and computer science. This is a discipline that we deal with a lot of emerging technologies, and the research that we pursue at EmTech and my own practice is dealing with emerging technologies and how can they solve emerging problems. This is the gist of how we see architecture as discipline, as a discourse and a practice in our day-to-day lives. I mean, looking back into the discipline of architecture, which was kind of synonymous to the built environment. Now architecture has evolved, kind of intertwined and blend with other disciplines such as computer science, material science, and the solutions that an architect can provide is just going beyond the architecture solutions. They can be urban solutions, material systems, design methodologies, computational workflows, and even sometimes software and applications. And this is something that us as architects and urban designers are equipped to propose and to solve problems that we're dealing with in our day-to-day lives. Today, I'm going to go through a few case studies and present this discipline from two different lenses, which I believe these two are two sides of the same coin, digital and physical. And through presenting different case studies, then I would try to bring them together towards the end of the presentation and provide how we see architecture as a hybrid method of physical and digital approach to the built environment and our day-to-day lives. If I tend to speak a lot and if I go beyond 45 minutes, just please stop me because I can just talk for like hours and hours. First, digital. Digital in this sense means the time before things become materialized or physical. Things become physically realized. That's what I call digital in this sense. And one of the big aspects of how we approach design and how we approach solving problems will be summarized into this realm of digital. I'm going to talk about a term that I think most of us are quite familiar with, which is biomimetic. In a very simple word, it means looking into nature, learning from nature, and finding solutions for our day-to-day life. These are four images of different buildings and structures that somehow get inspired by natural systems. So the idea of form following nature is not something new, and it's been around for quite a few times. Actually, from 50s and 60s by Otto Smith, it was coined by this person. But today I'm in the digital part of the lecture, which then I will try to tie it back to physical. I'm going to talk about a different principle. A form follows nature's process, and that process, which I am extremely interested in, it's my line of research and what we believe could help and push the boundaries of our design discipline is the evolutionary process. I'm not going to go in detail of what this process is in biology, but I need to just pull out some few important key points and terminologies in order to bridge some gaps between our own discipline and another discipline like biology. For those of you who are interested in this way of thinking, I haven't even started talking about this way of thinking, but these two books are extremely informative, seminal figures and authors in this discipline, computational design biomimetic, which I really recommend if you are interested to know more about this. And Evolutionary Architecture by John Fraser and Philip Stedman, The Evolution of Designs. All right, going back to our own mix of disciplines. So there are a series of biological principles that we architects are interested in, and the way that we can actually use those principles, abstract those principles, extract them from systems out there, and then understand them and pull them out, use them in a completely different discipline, is going through a bridge which is called computation, which now with these days advances and technological um, advances, it is allowing us to do this more and more in a more streamlined fashion, and it is becoming somehow a feedback loop between our own discipline and computation, that it is getting to a point that design and computation are becoming somehow one entity when we are talking about the digital realm of architecture and design. But what is this biological principles that I'm talking about? When I say form follows nature's process, what do I mean by that? That process is called evolutionary process. It's scientifically proven. It's been here before us. It will be here after us. It's just around us. Everything that you see around you is the production of evolution. Even us speaking to one another is one of the key productions of evolution. I want to play a video, and then after that, I will just pull out some information from this video.
It's the code you added, sir. The reveries. It has some
mistakes. Is the word you're too embarrassed to use. You ought not to be a product of a trillion of them. The evolution forged the entirety of sentient life on this planet using only one tool, the mistake.
I flattered myself we were taking a more disciplined approach here. I suppose self-delusion is a gift of natural selection as well.
Indeed it is. But of course, we've managed to slip evolution's leash now, haven't we? We can cure any disease, keep even the weakest of us alive, and one fine day, perhaps we shall even resurrect the dead, call forth Lazarus.
The term that I'm very interested in, I don't know if you guys could hear the sound. I hope you could. But it was a part of the show called Westworld. If you haven't watched it, I really recommend it. It's such an interesting show. There was a sentence that Anthony Hopkins was saying that evolution forged the entirety of sentient life on this planet using only one tool, the mistake. The reason I'm trying to open up the discourse of evolution because I want to pull out some important figures and components from this to see how this particular process can help us in architecture at the digital part of the topic. The mistake here is called the mutation. Basically, with all the complexities of what we see in nature around us in our environment, is the production of very important thing which is called mutation. Mutation is equal to mistake, is equal to changes in building blocks of the living things, and when they become in contact with their environment, these changes and these mistakes and mutations, some of them are becoming good, successful, they continue, and some of them are becoming unsuccessful and they will be deleted. um you might be Actually, this is a diagram that we all felt to our bones. This is the diagram of the mutation from COVID virus. This shows what are the successful mutations and what were the not successful mutations, and we could feel it with our bones because this is what we all could feel. And in the context of the COVID virus and the environment itself, this is a very simple example that could then be applied to the entirety of nature and evolution. So the idea of mistake, error, and the relationship that this mistake and error has with the environment. This process is actually very efficient. It creates a lot of variation, a lot of diversity, and it creates multitude of different behaviors and forms even within one species, which this variation is one of the important reasons of why species are becoming adapted to a constant changes that the environment imposes on them. And these variation, even in one species, well, actually was one of the important moments in Darwin's research on evolution, was that why a same species, for example, in this image, it shows the species of finch on the Galapagos Island, but the same species have different shaped beaks and different form beaks. And he was asking the question of why this is happening and how a same block, a building block, which is in this case this little bird, they take different forms and behaviors, and what is the relationship they have with their environment. And this puts forward another important question in this context, which is these differences, are they actually important or they're not important? Is it good to represent these differences through a single average? Does the average exist? Can we represent all of these butterflies with only one butterfly? Or the differences between these butterflies are more important? And why we are actually talking about differences and why we are talking about adaptation and different forms and behaviors. When we move forward scientifically, the progresses in genetic science, it became clear that even like with all these massive differences that species have to one another, their building blocks are actually very similar to one another. I mean, this image shows the part of the genome, the part of the DNA of a human being and a fruit fly that controls the growth of head, torso, and limbs are actually very similar and quite identical. And when we look at the larger context of the living species in nature, we see that a lot of the DNA and the building blocks of our own surroundings are very similar. But when it comes to contact to the environment, to the surrounding, the differences could emerge. Different behaviors and forms emerge in relationship and in conclusion of their relationship to their environment. This is a very good book to dive deep. If you want to dive deep into the topic of evolution, where does it come from? and how everything links up to the current advances in genetics, I really recommend this book. But going back to our own discipline, if scientifically proven, and if we could actually see that this process, evolutionary process, is an extremely efficient process, yet simple, to produce and to evolve forms and behaviors that are quite fit and adapted to their environment, I think it is very important for us as architects and urban designers who deal with forms and behaviors to look into this process, to understand what we can learn from this process and how we can translate this process back into our discipline. This is where we are actually going from one discipline to the other through a bridge of computation. With all of the complexities of evolutionary process in nature, it can actually be boiled down to four simple components: reproduction. And through this reproduction, a variation will occur. Through this variation, there will be a competition for survival. The ones who are fitter, who are better, who are well suited in the environment, they will survive. The ones that are not, they will not survive. And then there will be a selection of the ones to survive, and this loop will continue. Guess what? This is a very simple loop that could be translated to a series of algorithm, to a series of step-by-step recipe-like process to be applied in other disciplines. And surprisingly, this way of thinking and dealing problems has been around since 50s and 60s. The evolutionary computation, indeed, have been applied to different problems, from even music to social science to design, architecture, and engineering. The discipline itself, evolutionary computation, started somehow in a similar fashion to the evolutionary process and the theory of evolution in biology, because that theory started with two independent streams of research, one from Darwin and the other one from Wallace. They ended up getting to know each other, and then Darwin was much richer than poor Wallace, and everything has gone to Darwin. Evolutionary computation also is quite similarly to evolution in nature and biology, has been founded by these three independent research streams around a similar time of 50s and 60s. The one that we are quite familiar with is genetic algorithms, but it has other parallel research called evolutionary programming and strategies up until 90s and 80s, that they all came to the same umbrella of evolutionary computation. Now I'm taking us slowly from biology to computation, and then I'll go to design and architecture. Basically, the discipline of evolutionary computation, just like any other discipline, scientific discipline, always comes with different advances time to time. Every year, if you look at these reports, papers, articles, there will be numerous different algorithms coming to practice. And for us as architects who are non-computer scientists, when we look at this discipline, it's like, well, what do I use now if I want to use something in my own workflows? There are two important factors to put into evaluation when we want to choose something from another discipline, especially from evolutionary computation, to be used in design. We don't know how to use it yet, but there are two important factors. First is time. How long does it take for this process, which is the simulation or um, the algorithmic recreation of evolution that would happen in a short period of time in a computer? How long does it take in order to get to a point that it needs to get? We don't know what that point is. We'll talk about it. And how much variation that process will create for us. If you remember the slide of butterflies and seashells, this particular parameter, variation, is an extremely important parameter when we're dealing with these way of thinking in design. Well, going back to this simple diagram, which shows the link between three disciplines, biological principles of evolution, we found them quite interesting to evolve forms and behaviors that are quite fit to their environment. Guess what? As architects, we are dealing with forms and behaviors that they have to be fit to their environment, like buildings, master plans, urban designs. We found them quite interesting. So now we wanted to translate them back to architecture, to design discipline, and we kind of use computation as a bridge to help us to do this. Now going back to design and how this is going to help us to coming up with better design solutions is first us as architects to understand that every single design problem we're dealing with is coming from different perspective. Every single architectural problems, even in the seminar briefs in your studio, at the office, they all need to deal with completely sometimes opposing objectives. For example, like sometimes you're like coming up with a problem that needs to deal with structure, energy, price, material, and space all at the same time. And as someone like who traditionally was taught architecture, this is an extremely hard task. It takes a lot of time and resources to come up with a solution of such. But using biological principles and evolutionary thinking into the design process would help us to redefine the architect's role. If traditionally we used to look into the design briefs as a question that we are asked to come up with the answer for, designing a solution, now understanding and using these principles into the design process will change the game. We don't need to coming up with a single solution anymore. What we need to do, we need to design a problem, we need to design the environment, we need to design the relationships based on which, with the help of the technological advancements and computational powers, we can come up with the solutions. So what we are going to do and how this evolutionary process and evolutionary thinking will help us to solve the problem is to changing some gears, changing some perspectives. We don't need to come up with a single solution. Sometimes architectural problems, they have multiple different solutions. Sometimes there's no single solution that can fit all the purposes. A little bit going deeper into the change that this way of thinking will apply to our design process is traditionally we have a project, we are given a task, we do our research, we find the constraints, we perform brainstorming session either alone or with our team, and we come up with different options. But now things are different. We define the problem to ask from the computer or from our agent, from the machine that we are designing with. And that process will produce a series of different solutions that then us as designers are yet to decide to move forward with. What do I mean by this? I mean something like this. Some of you may have been not yet exploring algorithmic thinking, but this is a on the bottom of the slide, you see the Grasshopper canvas, which is the visual programming interface with Rhino and Grasshopper, which allow you to come up with different sets of relationships. On the top, on the other hand, you will see what this algorithm could create. Well, traditionally speaking, if I come to you as a client or as your studio tutor and say, hey, you have a design task to design an urban block that needs to fit and check multiple different boxes. I sit down for a month and think about how and in what aspect I can design my block to address these objectives. But now, with this way of designing and thinking, we do not need to think about the solution, yet we need to think about how to design or how to prepare the form and the geometry of the problem through a set of algorithms, then the machine or the evolutionary computation as the agent that help us to solve the problems could then explore different series of options for us. Now, what do I mean by this? Traditionally speaking, to find a solution for a problem, we sit down and we think about, all right, how to solve the courtyard relationships, how to solve the density, how to solve the exposure and ground floor area. And then we do sketches, multiple iterations, we choose one and we move forward. But when we apply evolutionary thinking to the design problem as an architect, we do not look for a single solution. What we look for a series of relationships through which the geometry of the problem is being created. And this geometry is going to be tested iteratively through the process of evolution that is simulated in computer. And then within each iteration, this process is trying to find a series of options, series of solutions that could fit the purpose of the problem. So there will be a collaboration in this way of thinking and designing between us, human, and a computer. And this will create a feedback loop that every time you design a problem, every time you design a series of relationship, computer will give you a series of results, and then us as humans need to understand those results, and then this back and forth creates a very interesting collaborative work between us and a computer, between us and a machine. This is not a linear process, this is an iterative process. And the tool that I have developed called Wallasey actually allow this to happen, allow this to create a symbiotic relationship and collaborative workflow between the designer and the machine or the algorithm or the computer, whatever you want to name it, in order to tackle a problem from different aspects and different perspectives, different objectives, and to come up with a series of solutions, to come up with an available options, then handing it back to us as designers to make better and more informed decisions. Something that is usually misrepresented about these way of designing and thinking is that, oh yeah, you're eliminating the architect. No, you're not eliminating the architect. Actually, you're making architect's life way harder, because now you're opening the doors of other possibilities of how a problem could be resolved with the perspective that goes beyond our intuition. It is becoming an objective approach versus a subjective approach to solve a problem. And for example, in this particular scenario, this is an old project. It's been a few years, but this is a very good example that the client was asking about a tower that they wanted to design. They only knew a series of numerical performances, and they were completely open with a catalog of different options that could fit the purpose. Well, when you have a series of objectives, when you have series of constraints, and then you want to design, or let's say, quote unquote, evolve a form that fit within those constraints, this completely check the box of evolutionary computation, because basically evolution produced forms and behaviors that needs to fulfill a lot of different objectives. And now with the power of computation, we could translate that to the design discipline. These are like these are different projects here and there that through studios I teach in different institutions that using this way of thinking in solving problems. And these are different examples to show that regardless of the scale of the problem at hand, these problems can be formulated from the objective perspective of evolutionary computation. And this doesn't mean necessarily that the designer will lose its sight or the designer will lose its significance. No. On the other side, designer will have way more important responsibility in designing the problem in a way that the collaborative machine could produce result. And this is also could be applied in any other design process. I mean, this, as long as you're dealing with a form, as long as you're dealing with an object that is going to be placed in an environment that needs to fulfill a series of objectives, well, you're here for a treat, because then you can use this system of thinking, which Wallasey will facilitate. I should say also, Wallasey is one of the tools that allow this to happen. It is quite unique in its approach because it's designed and developed by designers, but there are other tools out there that would allow you to do this as well. But what I would like to emphasize and highlight is that regardless of the problem at hand, when you have a designed object, entity, being something that has a matter and physicality in relation to the environment around it, this is a perfect approach to coming up with problems. Later on, through recent research, we actually dive a little bit deeper into the genetics of the design problem, because traditionally these processes are always represented by fitness function, fitness objective, fitness value, performance. What is a performance? No one has looked into the building blocks of this problem, the genetics. And through multiple research that we've done, we've understood that these actually provides a huge opportunity to link up these processes to other processes, such as machine learning, such as training neural networks, such as providing a way to understand the differences between the variations and the phenotypes and the geometries. Basically, the significance of this way of thinking is not only coming to a single point of contact to the end of the project that, hey, I designed this tower, I designed this master plan. The significance of this way of thinking is to apply this to a variety of scale, because this allow different scales to be linked up to one another. Now, this way of thinking, which is all in the realm of digital, nothing has been tangible yet. Everything was in the realm of abstraction. Now, let's see how this can be manifested to a real project. I'm going to go over a few build projects that we did recently here in London, and present how this way of thinking and this way of designing could help us to better design more efficient structures with more sustainable approach. This is a project that we collaborated with a studio called Hassel Studio, and ended up to become a pavilion here right in front of the AA in Bedford Square. The project starts with a research, with the theme of our sponsor Hassel, that, hey, we want to build a structure that is self-standing, is structurally viable, but use completely recycled timber pallets. So then we again took everything to an abstract mode, understanding what are the design principles and how to then translate these design principles to a series of relationships geometrically, materially, through tests and experiments, how to understand the requirements and constraints, and how to then come up with a way to convert these abstract design principles into objects and structures that could physically be realized. This process always is a back and forth process. This process always comes with a lot of tests and experiments, with a lot of daydreaming and brainstorming, with a lot of analysis, with a lot of different modes of understanding the performance of the project, even at the scale of its carbon footprint. But then to the end, when these design principles were completely tested and experimented, everything was translated again to a series of numbers and parameters that they have a meaning. They're meaningful to the project in its own context. When we have these design principles, when we have these parameters that are informed by the real life constraints, then it would be a great opportunity to hook it up to evolutionary computation. Why? Because this project, like any other project, required to address a series of objectives, and with understanding the ultimate goal, but not knowing what could the form be. This process would help us to explore different options, the options that will eventually completely optimize for a series of very important objectives, and then translate it back to its physical life. And this back and forth between understanding the physicality of the material, abstracting that physicality, abstracting that behavior, putting into the series of constraints, series of principles, series of codes, genes, whatever you want to name it, creating a series of constraints and environment within which your form, your structure could evolve is a great example of using evolutionary computation. Besides that, we also produced an app that could help us basically provide a lot of insight into the fabrication of the process. We used augmented reality to direct us where to place what, because things were quite different as we built, because it was just completely recycled series of timber pallets, different thicknesses, different behaviors, and we needed to have a digital blueprint with us along the way. And this app also provides some background history of the entire pavilion, and so on and so forth. And then after going through this whole iterative process of physical, digital, evolution, computation, evolution, then things become to be, because everything comes with a series of metadata. The form that you see comes with a lot of information, the information that were initially translated and to our digital workflow, and the digital workflow will then inform our physical process. And this is a time lapse of us assembling this project in Bedford Square. And yep. So this is one of the examples of how that way of thinking could help us to realize forms and behaviors that are fit for their purpose. And in this scenario, the purpose was structure that is built by recycled timber, structure that is built by woods that were in their second or third life, structure that is viable, structure that is self-standing, and then realize into a real life. What is very important in all of these processes is to not to end there. What we always do is we try to understand and find out the tolerances between this digital and physical sides of things. This is the scan of the pavilion overlaid onto the digital model of the pavilion to see how far we could actually get close to this process. And the pavilion actually won an award in Architizer, the collaboration category. The second example that is again the progress and the process of this way of thinking is a structure that we built a year ago called Flex from Rattingham, which is the current research that we're pursuing in EmTech right now. Again, by looking into nature, evolution has favored the fiber-like structures in complex living organisms. Many of these fibrous systems are involved in alignment of long and stiff fibers in parallel formation in multiple layers. This is also a very important principle that has been utilized in architecture in our own discipline. This is a project in Mannheim. And in EmTech, we explore these fibrous systems and structures. This is one of the recent completed theses in EmTech that dealt with the structural proposals for Yucatan Peninsula in Mexico to deal with flooding issue and hurricane issues. And whenever we started research, we do a thorough investigation of what's out there and to find a gap. Using ratting canes to come up with the structures has been used before, but what we wanted to do, we wanted to come up with a system that used bending as an opportunity to come up with structures of viable structures. We wanted to explore and highlight the differences between the stiffness of the objects and the stiffness of the materials, and how to use the material weakness, to be known as weakness because it's extremely flexible, as an opportunity. in this process, again, going back to digital and physical, there are a lot of different tests that is going to be done. There are a lot of different physical and digital prototyping, dealing with the material, understanding the behavior of the material, even sometimes creating a real life kangaroo or physics simulation to better understand how accurate our digital model is to our real life prototype. These are all our leads into getting to the level that we want to translate these principles into our digital workflow. Small scale models, different prototypes, these are all a way to understand and to abstract those design principles, those parameters, to eventually come up with a system that could be translated into the computer, that could be then part of a system to be hooked into the overall workflow of evolutionary computation. These are all, again, coming up a conclusion of a long experimentation phase of how to translate these numbers into the evolutionary system that could lead us to a viable structure that fulfill the objective of the project. And towards the end, the project was realized again after a series of intense experimentation in order to translate those principles that we identified through our physical prototypes. These are some images of the structure itself, and this is a team that ended up building the structure. This is again another example of how a way of thinking and a way of designing can help us to imagine, evolve forms and behaviors that are not necessarily known to us, but are the results of a rigorous evolutionary process. And this requires not only clicking of a button and hoping for something to come out of the end, this requires rigorous experimentation. Now, towards the end, I want to bring these two sides of the same coin into under the one umbrella of hybrid. This is how the research projects at EmTech are looking into the problems. This is how we perform and we use emerging technologies for emerging problems and understanding the design problems from different lenses and perspectives. Because architecture, regardless of the scale of the problem you're dealing with, always goes above and beyond in a way that it doesn't matter if you're designing an interior of the space or if you're designing an urban plan, there's always cross-scalar relationship between the problem you're trying to solve and other aspects of a larger scheme. In EmTech, what we emphasis and highlight is to coming up with novel architectural solution for existing design problems. Now I'm going to flip through a series of different, thesis projects from EmTech that was conducted in a few years ago. I'm trying to play, but it doesn't play, does it? Just give it a second. It's probably a large file. But these are the examples of how we in EmTech deal with opposing problems and emerging problems as architects and designers. How we look into the architectural problems from two sides of digital and physical, and how everything comes together towards the final phase of the project. Unfortunately, I'm having a problem to play these videos for some reason. Excuse me. Very strange. If you allow me, I'm going to stop the share just for a second, just to see what happened here. Yep. All right. Okay. I'm gonna get out of the um I needed to get out of the presentation mode. Sorry. Yeah, these are different projects that was conducted in EmTech, and I'm just going to let them play and pick up on a few important aspects of how these projects were realized. One of the key ways of thinking that we try to pursue in EmTech is to tackling the problem from different scales and understanding the relationship of this the problem that will create with its environment. This causes a rigorous experimentation from different scales, from different aspects, and these problems will then create a hierarchy of design solutions for a given problem. Um, in EmTech, we try to deal with existing emerging problems such as flooding issues, desertification issues, density issues, and using these methods and techniques to come up with meaningful and novel architecture solutions for these problems at hand. Particularly, for example, this project, which then eventually to become a complete software and application, was dealing with the issue of exclusivity and inclusivity in the public locations and public plazas here in London. They particularly picked one of the public squares and developed an app that linked up with a physical object that would allow people and users of citizens of the neighborhood to experience exclusivity in a public space. The mechanics of how this was realized, it's in the thesis, it's online, but this is just an example of how these emerging technologies could be used for these emerging problems. Another project here is the dealing with the housing crisis and densification of Hong Kong and coming up with a way to coming up with a way and a solution that allow housing projects to be adaptable, to be suited for multiple purposes, and to evolve with the occupant and the user's needs. Again, this is one of the emerging problems that was identified by our students, and then it ended up to become a thesis concluding to a material system and a proposal of a housing project. The other project is the project that I was just talking about, looking into the flooding issue in Mexico, Yucatan Peninsula. Our students looked into this issue from different perspectives of urban planning to material system and coming up with a modules, housing, and evacuation path that use local materials and enabled the fast and rapid production of them after the issue of flooding hit the space. The other one, which is the last one I'm going to end my lecture with, is looking into pollution. Again, another emerging problem. And they proposed a series of modular aggregation that could attach to different surfaces and the built environment areas across the context that they were investigating here, in this case, London, to help with the pollution issue, at the same time creating a platform to allow citizens of the city to participate in solving these issues. Again, the problem was tackled from different perspectives, from different scales, small scale material experimentation, all the way down to the larger scale urban planning. And within the case of dealing with these different scales of investigation, it's always going back to the idea of an architect is designing the problem, and with the help of technological advancements and material advancement, the solution is going to be evolved and proposed. And dealing with a problem from different scales requires an architect and designers to be mindful of the impacts of each scale to the other, from material phase, and how even a simple choice of a material can have an impact to the larger aggregation, even at the scale of the urban. And this is what we try to pursue in EmTech, and what we try to actually tackle every design problem in our practice is to dissect the problem into its components, understanding what the problem is, how to redesign the problem, and then again, with the help of emerging technologies, to coming up with the solutions. I mean, these emerging technologies sometimes are digital, the workflows. Now we are talking about generative AI, which is like a very buzzword, but at the same time, it has a significant impact of the way that we design and we come up with solutions. And sometimes these emerging technologies are physical computing, robotic fabrication, digital fabrication. As an architect, I think it is imperative to understand these changes, these advances, because then these advances would help us to come up with a better formulation of the problem that we are dealing with. And always, in both the research projects here at EmTech, the build projects, the generative workflows are not only the answer to the question. The generative workflows alongside with analytic workflows are basically two wheels of a machine that would help us to get to the problem and get to the solution. Having said this, I'm going to end my lecture with this image of the butterflies and digital butterflies. Again, highlighting the fact that we are at the forefront. I think we architects should be at the forefront of these changes in technology, and we can take advantage a lot from these changes, and it's our responsibility to use them. Otherwise, well, yeah, one day we might be irrelevant. Thank you.
Thank you, Dr. Showkatbaksh, for such an inspiring and thought-provoking presentation, really.
Thank you.
Let's open the floor for questions. Please feel free to raise your hand, or if you're in person, or type your questions in the chat if you're joining us online. I can start with my own questions until maybe.
Sure.
Okay, but I guess we have some questions in chat. No. Okay, so you talked about using genomes as part of, I'm rephrasing it myself, please, correct me if I'm wrong, as a part of parameterization of the architectural problem. So a few questions arise, but one of them is that how do you think we can proceed with the decision making? So we did the parameterization, we did the analysis, we did the optimization, but now that we have the results, and based on my own experience with your plugin, we are going to have different type of results based on different type of results in each design perspective. So then what would be the next step to find our like not perfect, but I guess the most fitting solution?
Well, yeah, this is a very common question when we're dealing with generative design. When I say generative, means like things that are generate. We generate generative design. It's always the question of, I think the answer lies in better understanding what the generative design is. Generative design is not supposed to give us the final answer. Generative design is supposed to only give us a better look at the problem. The problem that if without evolutionary computation, we might only be aware of a very small part of the design space. When I say design space, I refer to all possible solutions for a given problem. Without this approach, the smartest person on the earth could actually approach only a part of the design space. But the generative design would essentially help us to better understand the problem. Now, how to proceed from that phase onward is again going back to our own intuition. And we can always be objective. We can always have multiple layers of analysis to filter solutions to get to the phase that we want to get. But at the end of the day, what I'm going to say actually contradicts what I just presented. At the end of the day, we're going to build one building. At the end of the day, I'm an architect and I'm gonna choose something which fits all the purpose, check all the boxes, but something that I intuitively like. I mean, when I say like, I refer to a subjective preference. So it's not either or, it's both. And we have to be aware of this fact that generative design is not the answer. It's just the solution. It's just helping us to better see the problem. And then it's our design intuition that would allow us to make good design decisions. Yeah.
I think that explains a lot. And probably we can also call it maybe a way to explore geometry, the way we haven't even thought about. Thank you.
Yes.
I have another question about the first pavilion you showed us. You mentioned using again evolutionary analysis to design, but I was like, I had this question that because the design is going to happen in maybe 3 scales, maybe a overall scale, and then we go into fabrication details. And so the question is, when you're doing the analysis, are you also incorporating feedback of details or detail design into your analysis to have your materials have a better performance based on the details and assembly process? And how do you find it? I mean, and if yes, do you find it useful, or how can you incorporate it here? Yeah, thank you.
Yeah, I think when we're dealing with digital fabrication projects here, it's a very hard task, but at the very early on, we need to think about all aspects. Connections, joiners. Actually, what we say that joiners and connections are part of the global form. They are not something separate. And this actually, this particular thing that you ask, it highlights a very important thing, which is all of these processes are iterative. Look at this diagram. This diagram, I don't want to say all happen at the same time, but somehow all of it happened in more or less parallel time, and each phase of the project was informing another phase. Halfway through the project, a component, when I say a component, not necessarily a physical component, a part of the project need to be updated and changed, and it fit back to the beginning of the project. So this again highlights another important fact of iteration, iterative workflow. It's not linear. I think we all quite familiar with the design work, and the design work is always iterative. With these tools and technologies, this iterative work is being more streamlined, but I think it won't change. Even with the AI and Gen AI, I mean, I'm just gonna give an example of this image generation diffusion models. I mean, how many images you generate for one go? I mean, everything is iterative. And these tools only help us to have a better control over these iterative workflows. Yeah.
Yeah. Yeah, can you say...
Hello. First of all,
Hello.
thank you for your presentation. It was really good. And I have a question. I want to ask you, please explain more about the project related to exclusivity and inclusivity. I want to know that in which aspect these two terms gonna work. It's related to the human interaction with the built environment, or it's related to the social experience. And may I ask you to please explain it?
Absolutely.
Oops, thank you.
Yeah, sure. This is actually I can share with Sina, if you're interested to know about more about the thesis. The thesis are online. This project actually deals with a very interesting aspect of um, the public engagement from different stakeholders, and they come up with a proposal of a deployable structure that could allow to be adjusted and adapted with user input to enable different interactions with people. I mean, I'm going to go over here. I mean, these are over here. This is the part of the application that every single person could have access to when using that public space. These are the modules that by the stakeholder who was in charge of the project, for example, here, the city, the mayor, would facilitate to people to use, and then people with their evaluation, subjective evaluation, could evaluate the space that they want to spend time within. And then this could be open up to other stakeholders and public people, public audience in the space. This dealt with an issue of engagement with different stakeholders. Actually, this project was in the middle of the COVID, so this issue of exclusivity and inclusivity was kind of like a big issue here, I think everywhere. And the way that the digital world and the physical world came together here was through the context of the platform they developed to enable change into the physical built environment within which then the subjective experience could be changed and enhanced. This is a very simple theme of the project. And how they have done this? Well, it's 6 months of massive work computationally and physically. But if it has been put into test, yeah, very small scale survey. But yet again, this project stayed at that level of development. But I can share with you the complete thesis online if you're interested more about the topic.
Thank you very much. Yes, please. Thank you. I appreciate it.
Sure.
Hello, my name is Tofi. Thank you so much for your presentation. You mentioned proposing solutions for widespread pollution in a city like London. What would you hypothesize generative design would suggest for an even more polluted area like brownfield lands, for example?
Well, yeah, I mean, let me actually go to that project so I can talk over the project. Yeah, this project looked into different aspects of how to deal with this issue. The first one was the material aspect. What kind of material they can propose to actually capture the pollution, the pollutants in the air through geometrical properties and the formal properties of the modules at the same time through the material characteristics, because the modules that they have developed, these modules, there were multi-layer modules coming up with plant species and porosity that would allow to capture the pollutants in the air. And how generative design came to play in this particular aspect was to what could be the best and what are the options of this form that could enable the best performance. The performance in this case was capturing the pollutions in the wind flow direction, making sure the material itself is physically realizable, making sure the plant species that they decided to grow on these modules would have enough spatial requirements, and all of these objectives, again, when you sit down and when you put them down into the design principle and translate them to a series of objectives, it fits purpose, it fits very well within the context of evolutionary computation. Now, how to apply this to other contexts, then it's up to us, or it's up to you actually, how to translate the requirements of that context into a series of performance measurements in order to then inform these generative workflows. We architects loves quality. I want to have a beautiful building. I want to have a good looking, but these are great, but these do not necessarily mean anything in computer. We have to find a way to translate them and to convert them to numerical performances. So every context on its own has its own unique problem, has its own unique definition.
Thank you.
Sure.
Okay, so we have a few questions in the chat as well. I'm going to go ahead and read the first one. I have a specific I'm sorry, but I can't read her name or his name. So, Jing Fengyu. Fengyu. I have a specific question about Flex project. So the question is, how did you analyze the bundled rods with torsion and pre-bending, especially the moments are related to the discrete materials, and how you build the structure models in digital, like duplicating multiple components in the same position?
That's a very good question. The only way to do this to calibrate our digital model with the physical experiments. And the very first thing we did, we tried to basically recreate the physics engine in real life. I mean, if you're familiar with Grasshopper, Grasshopper has a physics engine called Kangaroo. On the left is a Kangaroo simulation, and on the right is our own. It's me actually being happy that the simulation is actually acting the same as the digital workflow. There's no other way. That's what the hybrid mode of physical and digital and two sides of the same coin is very important, because one is going to inform the other. Doing a lot of tests, doing a lot of bending tests, doing a lot of bundling tests to understand how far the material can be pushed. That's it. It's always coming with experimentation. And we always need to calibrate our digital models with our physical prototypes. Otherwise, there is no other way. Look, we even did a lot of experiments here. I just passed through this very fast, but we did an experiment, a very simple load test of this rattan bundled canes to understand the Young modulus. Then understanding the Young modulus would help us to put in parameters into our digital model. When we did that, then we needed to actually calibrate that model, because that number didn't mean anything in the digital world. And we had to just fine tune it in order to make sure these two behaviors are the same. Again, iterative workflow.
I help you. Okay. Ali is in the chat said, thank you very much for this insightful presentation. My question is, when dealing with a design space that involves recursive algorithms like agent-based modeling, how accurately can an evolutionary solver like Wallasey export that space and generate optimal solutions? Is there a risk that some of the feeder generations might be missed during the evolutionary process, especially given the complexity and potential of emergent behaviors in recursive systems? That's a very good thing.
That's a very good question and very technical. And the answer is yes, there is always a risk. And that's why we need to do a lot of analysis. That's why we have to take advantage of all of these analysis that Wallasey is here to provide. Because without understanding what's happening in the model and what's happening through the evolution, by looking at the objective truth, we won't know if the design space is explored properly. So yes, there is a risk, and the way to actually find if we are actually in danger of missing out a part of the design space is to always do the analysis. I mean, on its own, it takes hours of lecture to better understand, okay, how to read these graphs. But yes, there is a way to do this in Wallasey. because we always need to have a baseline, and the baseline is objective truth, and the objective truth is our objectives. Yeah. Actually, there's a very interesting book where I just said about objective truth. There's this scientist called Donald Hoffman. It's called When Evolution Tricked Us. We don't even know what objective truth is actually. So let alone the computer and the world. See. So yeah, I mean, it needs analysis, Ali. We have to do a lot of analysis.
Yeah, I think that's all. Thank you. Thank you, Dr. Showkatbaksh for joining us today and for your detailed responses and very inspiring research. It was a privilege for us to have you here. And before we wrap up, I wanted to remind you all that we are going to record this. We have recorded this session, and we're going to share it on Hi-DARS YouTube channel. So you could, if you want to revisit the lecture, or if you want to share it with your peers. Thank you joining us for Dr. Showkatbaksh and everyone else, and we look forward to see your research and the development of your research so far. Thank you.
Thank you for having me. Have a great day. Bye bye.
Oh, yeah.